Have you ever looked up at the sun and wondered how it produces so much energy? It's not burning like a fire. It's doing something far more powerful, something we're trying to recreate right here on Earth. This is the story of nuclear fusion, the ultimate energy source that could change everything for humanity. You've probably heard of nuclear energy, but that's usually nuclear fission. Fission is what our current nuclear power plants do. They split heavy atoms, like uranium, to release energy. It works, but it creates long-lived radioactive waste and has a risk of meltdown. Fusion is the exact opposite. Instead of splitting atoms, fusion combines them. It takes light elements, like hydrogen, and smashes them together under immense heat and pressure to form a heavier element, like helium. This is what happens inside the sun. Its immense gravity crushes hydrogen atoms together, fusing them and releasing an incredible amount of energy. How much energy? Well, Einstein's famous equation, E equals mc squared, tells us that a tiny amount of mass can be converted into a huge amount of energy. In fusion, the resulting helium atom is slightly less massive than the hydrogen atoms that created it. That tiny bit of lost mass is converted directly into pure energy. This process is why fusion is often called the holy grail of energy. It's clean, it's powerful, and its fuel is nearly limitless. So, if it's that great, why aren't we using it? Well, recreating a star on Earth is difficult. The sun has a massive advantage, its own gravity. Here, we don't have that luxury. We need to find other ways to generate the mind-boggling conditions required for fusion. We're talking temperatures over 100 million degrees Celsius. That's hotter than the core of the sun. At these temperatures, matter doesn't exist as a solid, liquid, or gas. It becomes a fourth state of matter called plasma, a superheated soup of charged particles. How do you contain something that hot? You can't just build a box for it. It would instantly vaporize any material it touches. Scientists have come up with a few clever solutions. The most famous is the tokamak. Imagine a giant hollow donut wrapped in powerful magnets. These magnets create a powerful magnetic field that traps the hot plasma, keeping it suspended in the middle, away from the walls. The largest tokamak in the world, called Guider, is currently being built in France by an international collaboration. Another design is the stellarator. It also uses magnets to contain plasma, but instead of a simple donut shape, it's a twisted, complex, almost sculptural form. The idea is to create a more stable magnetic field, which could allow it to run continuously for longer periods. Then there's a completely different approach called inertial confinement. Instead of using magnets, this method takes a tiny pellet of fuel and blasts it from all sides with some of the world's most powerful lasers. The intense energy blast implodes the pellet, creating the temperature and pressure needed for fusion to occur in a tiny, fleeting moment. This is what the National Ignition Facility, or NIF, in California does. All of these approaches face enormous challenges. Maintaining a stable plasma at 100 million degrees is incredibly tricky. It's like trying to hold jello with a net of rubber bands. The plasma writhes and tries to escape, and any instability can cool it down and stop the reaction. Then there's the biggest challenge of all: energy gain. For decades, every fusion experiment on Earth has used more energy to heat and contain the plasma than the fusion reaction itself produced. To be a viable power source, you obviously need to get more energy out than you put in. This is called achieving net energy gain, or ignition. And this is where the story gets really exciting. For the first time in history, we've done it. In December 2022, the National Ignition Facility in California announced a monumental breakthrough. They fired their lasers at a fuel pellet, and for a brief moment, the fusion reaction produced more energy than the lasers delivered to the target. It was a net energy gain. This was a proof of concept, a Wright brothers moment for fusion energy. It proved that a controlled fusion reaction that produces more energy than it consumes is physically possible. And the breakthroughs aren't just happening there. We're seeing incredible advances in superconducting magnets. These new, more powerful magnets can create stronger magnetic fields to confine plasma more effectively and efficiently, which could lead to smaller, cheaper reactors. This progress isn't just in government labs anymore either. A whole new ecosystem of private companies has jumped into the race. Companies like Commonwealth Fusion Systems, Helion, and T Technologies are attracting billions in investment and are moving at incredible speeds, experimenting with innovative designs and accelerating the timeline. So why is all this effort worth it? What makes fusion so promising? First, it's incredibly clean. The main byproduct of the most common fusion reaction is helium, an inert, non-toxic gas. It produces no greenhouse gases, so it doesn't contribute to climate change. Second, it's safe. There's no risk of a runaway chain reaction or meltdown like in a fission plant. If the plasma confinement fails, the reaction simply stops. Third, there is no long-lived radioactive waste. While the reactor walls can become radioactive over time, the materials are chosen so that this radioactivity decays in decades, not millennia. And the fuel? It's abundant. The main fuels are two isotopes or versions of hydrogen, deuterium and tritium. Deuterium can be easily extracted from seawater. A single bathtub of water contains enough deuterium to power a home for a year. Tritium is rarer, but it can be produced from lithium, which is also abundant in the Earth's crust and oceans. The fuel for fusion power is so plentiful it could power our entire civilization for millions of years. What's really pushing us over the finish line is the convergence of fusion science with another revolutionary technology. Artificial intelligence. AI is becoming an indispensable tool. For example, Google's DeepMind developed an AI that can control the magnets in a tokamak in real time to predict and prevent plasma instabilities before they happen. That's a huge deal. Machine learning algorithms are also being used to analyze vast amounts of experimental data to optimize reactor designs and discover new ways to run them more efficiently. In the future, quantum computing could even simulate the complex behavior of plasma at a level we can only dream of today, dramatically speeding up our learning process. If we succeed, the impact will be staggering. Imagine a world with cheap, abundant, clean electricity for everyone. It would be the greatest transformation in human history. We could decarbonize our entire planet, ending our reliance on fossil fuels. We could power large-scale desalination plants to provide fresh water to arid regions. We could run heavy industries like steel and cement production with zero emissions. It would even revolutionize space exploration, enabling fusion-powered rockets for rapid travel across the solar system and fusion reactors to power colonies on Mars. It would fundamentally end the concept of energy scarcity forever. This brings us to the big question everyone asks. When? For decades, there's been a running joke in the physics community that fusion is 30 years away and always will be. But for the first time, that might not be true. With the recent scientific breakthroughs, the massive private investment, and the power of AI, that timeline is genuinely shrinking. Many experts now believe we could see the first commercial fusion power plants connecting to the grid sometime in the 2030s or 2040s. It's no longer a distant dream. It's becoming an engineering challenge. Think about the world that creates cities powered by clean, limitless energy, global energy independence, rewriting geopolitics, and reducing conflicts over resources. What ethical questions arise when energy is no longer a constraint on human ambition? This isn't just a science project. This is the quest to build a star on Earth, to harness the power of the cosmos, and secure a sustainable, prosperous future for humanity. We are closer than ever before. The next few decades will be the most exciting in the history of energy, and we all have a front row seat. Thanks for watching, and if you found this exciting, make sure to follow for more stories about the future we're building.